if you can reach back all the way into your mind into introductory calculus, you remember that we can describe the integral by slicing up a function in pieces and then taking these rectangles for each piece and summing up their areas. And that will approximate the integral over the area. And then as we make those strips ever thinner, those rectangle approximations become better and better and better, and they converge into the value of the actual integral. And what we find is when we're dealing with functions of multiple variables, we have a very similar description, but we're usually getting volumes. So if we're getting volumes, then we don't have a rectangle we're dealing with. We have like a rectangular prism that we're dealing with. So instead of a sort of a length times a height, what we have is sort of an area of a base times a height. And so to do that, what we come up with is instead of sort of that delta x that you might have dealt with here, we have this delta a, or this kind of differential area. So going and saying this a little more explicitly, let's say I have some surface z, and it's always greater than or equal to 0, and we only care about the cases where x is positive and y is positive, so that quadrant of the inputs. If we want to find, and we're really just doing this to establish a very simple case, and we're going to expand it later. If we do that, then to find the volume of the, let's see, did I say, yeah, okay, make sure I said volume. The volume between the xy plane, or that z equals 0, up to the surface, we want to find that volume. What we do is we take these delta a's, these little area regions here, and we would, for all these pieces, we would construct these rectangular prisms and we would sum them up. So what we would do is we would take a function height somewhere and an area. So if we go back to the idea of a Riemann sum for one or single variable functions, you could take the left height, you could take the right height of the function, you could take the midpoint of the function, right? You took some function value in that strip, whether it's on the boundary or not. And in this case, it's the same idea, except that the function value could come from the boundary or anywhere inside the area. So we say that the volume is approximately the sum of all of those differential areas times the height of the function in that area, or the value of the function at some point on that area. Now, if we want to find the volume explicitly, what we do is we set up this limit. So you take the same idea here, and then there's a little bit of a trick here. Notice that this is still n. Usually when you have a limit, that's like n goes to infinity. But in this limit, we have this sort of norm, like almost like the way you think of a norm of a vector, of this delta goes to 0. Well, what they're doing is they're basically saying, delta, I'm going to describe delta as the largest diagonal of any of these little area pieces. So all I'm saying is that this is the limit as those diagonals get ever smaller. So effectively, instead of this grid, now I've cut it, and I can slice and slice and slice, and as I slice ever more, that eventually slices, or those eventually become, infinitesimally small, and the approximations become ever and ever clearer, which finally results in this, what we call a double integral. Now, this is different than an iterated integral. This is not an iterated integral. This is a double integral. It really just means that the thing we're differentiating with respect to is a differential area instead of sort of a differential length. And we're going to develop techniques that allow us, for some double integrals, most double integrals, to be able to transfer them to iterated integrals. But I just want you to know that this concept is not the same as an iterated integral. They behave a bit differently.